title is about polynomial calculus in QBF, circuit characterization and lower bound. Let's welcome Luke.
Thank you. Does it work? Do you hear me? Perfect. Yes, thank you for the introduction. In the last talk before the lunch session, Mina already introduced a bit of proof complexity. Here in this session, we will focus mainly on proof of complexity. You could say only on proof complexity, but for different systems. Indeed, as the title says, it's mostly on polynomial calculus in QBF. This talk is based on a joint work with Olaf, Tim, and Kasper, and is also based on a paper which will be at MFCS next week. As a short introduction, what is polynomial calculus? Polynomial calculus in its core is a proof system for refuting common roots of a set of polynomials. So in its core, it has nothing to do with either QBF or even SAT. The lines of a polynomial calculus proof are just polynomial equations, p equals 0. So the right side of the equation is always 0, and the left side is some kind of polynomial equations. The polynomials are over some kind of fixed field f. You can assume, if I don't say anything else, it's some subfield of C or a finite field. Most of the time, it doesn't really matter. And an important point is the proof size is the number of monomials and not the number of lines compared to some resolution proof or something. Here's a short example. I won't give all the rules of polynomial calculus because they're not really important for this talk. But here's an example. We have two polynomials, and we want to show that both of those polynomials don't have a common root. And we can multiply one of those polynomials by a variable, in this case y. We can multiply it by a constant, and we can add those. And the polynomial calculus refutation is just a refutation. If you get 1 equals 0 at the end, it's an obviously false statement comparable to the empty clause in a resolution proof. You can use a polynomial calculus as a propositional proof system for SAT, and this is also studied. And you just have to add a bit of Boolean semantics. So you map the true value to 0 and the false value to 1. That might seem a bit counterintuitive, but it makes it easier with the form equation equals 0. So 0 equals 0 is obviously the true statement, and 1 equals 0 is the false statement. So this mapping is easier. Then you have to add the Boolean axioms, which are just x times x minus 1 equals 0. Those axioms are true if x is 1 or 0, and for everything else it is false. Now, the next step are the complementary variables. The problem with these encodings, how I presented them, is that some CNFs cannot be efficiently transformed if you just take the variables and 1 minus the variables for the negation. Because, as I said before, the number of monomials is relevant. So if you have a long clause which just consists of the negations of literals, you have 1 minus x1 times 1 minus x2 and so on. And that's a lot of monomials if you take it in normal form. So there are complementary variables, x dash, which just mean the complement of x. And to ensure that it really is the complement of x, we have those axioms, here, x plus x dash minus 1 equals 0. Oftentimes, if we have those complementary variables, it is also called PCR, polynomial calculus with resolution, but it is here used quite interchangeably. So I always talk about the version with these variables. And as I alluded to earlier, it can be used as a proof system for unsatisfiable CNF. So you take each clause individually, translate it into a monomial or in a polynomial, but they are always monomials, and you get a PC proof of those, and it shows that a CNF is unsatisfiable. Now, what are QBF? I don't think I have to explain it too much because, well, we're in a QBF workshop. But an important thing here is perhaps for the universal quantifier. I've written here that for all u, q is true if both q with u equals 0 and q equals 1 is true. These are for the Boolean setting, these are all the cases, so it's obvious. But in the algebraic system, it is theoretically possible that such a variable can have different values, which are not 0 or 1. But our definition for the universal quantifier is still this one. So it's still only 0 or 1. Well, the rest is known. The games are also known. A counter model for a QBF. So we are always talking about false QBF here. So there are, of course, for true QBFs, there are models. For false QBFs, there are counter models. I will reintroduce them because they're quite important for this talk. So a counter model is just a winning strategy for the universal player. So each universal variable gets a function for all the existential variables before it in the quantifier prefix. Well, in this case, you can set u to not x1 and u2 to x1 or x2. It is, well, easily verifiable that is indeed a counter model. Okay, now we have all the things we need. We have polynomial calculus, we have QBF, and we want to combine those. There is already a technique to lift line-based systems, line-based propositional systems to QBFs. This technique is not new. The idea is simply we take our line-based system and we add an additional rule, the universal reduction. So if you have some kind of line where u is a universally quantified variable and there's no other existential variable that is right of u, while right is with respect to the quantifier prefix, then we can just set a value for u. So u equals 1 or u equals 0. Now, perhaps the more special thing here is the semantic entailment rule. We can just get another line in the proof if it is semantically entailed by all the previous lines in one single step. Now, this is, of course, a really strong rule. If you have just a propositional statement, then we are finished in just one step. But we use this to get a genuine QBF hardness, because if we have any lower bound for the polynomial calculus in a propositional setting, it is automatically directly a lower bound if we add this for all reduction rule. And that's not too interesting. But since this is just a simplification, any lower bound we show for this version obviously also holds if we don't have the semantic rule and just the normal rules for PCR. Yeah, I have a short example here how such a QPC refutation can look. And here we have the axioms 2 times. We can directly reduce u2 because u2 is just at the right side of the quantifier prefix. And on the left side, we set u2 to 1. On the right side, we set u2 to 0. Get both of those. With a semantic entailment step, in this case, it's just a single PC step, but it doesn't really matter. We get u1 minus x1. And remember, the lines are always implicitly equal 0. Just the equal 0 is not written. And then we repeat this with u1. We can now reduce u1. So we get 1 minus x1 and minus x1. And simple just one step. So we get a 1 equals 0. And it's a refutation. So now we have a proof system for QBF. And as is often the case in proof complexity, our goal is to provide a class of QBFs that require exponential size proofs in QPC. Now, lower bounds are always quite difficult because we have to argue against every single proof. So a technique is needed. And this technique is based on decision lists, especially on a unified decision list, which were also introduced for the resolution case. So for Q resolution or QU resolution, with the oracle, it's the same thing. The difference between decision lists and unified decision lists, perhaps I should say before that the decision list should calculate the counter model. Normally, if you have any proof, well, not any, but in most of the proof systems, we can, with strategy extraction, we get a decision list for each of the universal variables. The difference to these unified decision lists is, in this case, we want to set all universal variables in a single step. So we don't have a decision list for every single universal variable, but one for all of them. So for our example from before, This, for example, is a unified decision list for terms. Now we want to adapt this to a polynomial decision lists or polynomial unified decision lists, but it gets quite complicated, so we just call them PDLs, polynomial decision lists. We do exactly the same thing, except our queries are polynomials. Our queries are polynomials, and our answers are still settings of universal variables. Now, note that the queries all have the form polynomial unequals to 0. It is more or less the same thing as in the term decision list above. We need the negations of the lines of the proof system we had. So here we test if some polynomial is unequal to 0, then we set the universal variables. Else, we test the next polynomial, and so on. Now here's a bit of a more formal definition, but I think I've already said everything. So the queries are polynomials. They are true if the polynomial is not equal to 0. The assignment is complete to all universal variables. And the calculate function must be a valid universal strategy. So it is syntactically not clear here that the universal variables can't depend on some existential variable which is right of it in the quantifier prefix, but this is just a semantic restriction that reinforce. Some important measures comparably to PC proofs. The size of a PDL is the total amount of monomials in the queries, not lines. And the degree of a PDL is just the highest degree in any of the queries. And our main result is to connect the proof sizes of QPC to the sizes of these PDLs. And what we have shown that if we have a QBF with a limited quantifier alternation depth, so it must be constant, and then both PDLs and QPC are p-equivalent. If we have any QPC proof, we can extract a PDL in polynomial time and vice versa. To get from QPC to PDL, like I said before, we use a slightly modified strategy extraction to get blockwise decision lists. And then we use a technique called direct product to get these blockwise decision lists into a PDL. These blockwise decision lists in the case of Q resolution was absolutely no restriction. In the case of PDLs, we have to be a bit careful, but in the end, it does work out. Blockwise decision list, I don't think I defined it, and you can't see it here, just means we extract a decision list that assign all universal variables in a single block. So not all of them, but all of them in a single block. Now the technique of a direct product is quite simple. We have here two decision lists for two different blocks. In this case, it's just one variable each because the blocks are quite small for this example. And we just combine every line with every other line. So you take here the first line and for both and multiply them together. And in the second line, everywhere there is like a U1 in it, we just use the value from above and set it in. So we do that for every combination. In this case, there might be redundancies, but we don't really care. Because if we know we have just an alternation def for the quantifier prefix of d, then this is a polynomial blow up. So in the other direction is a bit more involved. And I won't really go into the proof here. But the idea is we start at a PDL and slowly extract a proof from it. But I have a slide for that, but I will skip it. So now we have our theorem. And this is actually quite a nice theorem if you think about it. So we have a circuit or some kind of weird circuit with this PDL, which is has a polynomials, but at the end is some kind of circuit class, and we have our proof size. And both of them are really polynomial equivalent. In the propositional case, such things are not so clear. So, well, okay, we have this corollary. If the counter model requires a large PDL, then it requires a large PC proof, but that's more or less what's in the theorem. What remains to be shown is, well, this characterization is nice and all, but we need lower bounds for the PDL. And for this, we use another technique that's really known in the propositional case. It's a size degree technique. And the size degree technique, in this case for propositional polynomial calculus, is known since 1999. And it just says that the size of the smallest proof is exponential in the degree of the proof with the smallest degree, more or less. You can see the exact formula here. And it turns out that this result also works one-to-one on PDLs. So if you can show we need a high degree for a PDL, we directly know that a PDL must also be long. Now we have also, from the result before, we know that long PDLs equals long PC proofs. So we have a technique to show long PC proofs, or QPC proofs in this case. We can also take the size degree relation and directly transform it to QPC, so we don't have to do it over the PDLs. There's an additional factor to d to the power 3 down there, but if we have a limited alternation depth in our family of formulas, it doesn't really matter. Oftentimes, however, it's quite a bit easier to discuss on the PDLs because they're quite a bit more intuitive than the proofs, so we use both a bit. Yes, proofs not so important. Yes, that's what I said. So we show that a PDL requires a high degree, and then we know that the function, yes, the degree of a PDL is just the highest degree in any of the queries. Yes. But an important fact that's missing here is, okay, we have a function that requires a high degree PDL, but it's just, the PDL just computes the counter model and not the formula itself. So we need a way to, if we have a counter model, to put this into a QBF. But it's actually quite simple. If our function f is the function which we know requires long PDLs, we define such a sigma-free QBF QF here, where we have just a single universal variable, and the t variables are just helper or auxiliary variables for the Zeithin transformations, and we just say, okay, u is unequals to f from x. So it is directly clear that to win, the universal player has to calculate f. And f is also the only universal strategy, and as such, the only counter model. So we have this size degree relation, and we can use it. What kinds of formulas can we use it on? An example, for example, are the majority formulas. Those just ask if we have a set of n existential variables, are more than half of those set. And we could show that in any field, the minimal PDL degree of this formula is at least n over 2. And as such, it requires large size, and QPC proofs of Q majority n also require large size. Similar things can be done for the parity formula or the mod functions. So parity just calculates the parity of all the variables, and the mod function is something quite similar, only a bit more general. So it is 1 if the sum of all these variables modulo k is 0, and else it is 0. And in subfields of C, it is really important which field we are using for our PC proof. The minimal degree is 1/2 times n over k minus 1. So if we take mod 3, for example, it is 1/2 times n over 2. And so in subfields of C, we require exponential PDL size, and as such, exponential QPC proofs. The subfields of C here are very important because if we have a finite field fp and want to calculate the mod p function, it is of course quite simple. We just add all the variables, and since our field is mod p, this line is exactly 0 if the sum of the variables is 0. Yes, this is the proof sketch for why this works. I will skip it. This size degree technique works quite well on those formulas we have shown, but it can't really show everything. To show the limitations of this technique, we have two formulas here. This is the square majority formula, SQM, and the row formula. What these formulas calculate exactly is not really important. I mean, the formal definition is here, but it's not really important. What is important that both of these formulas have n squared variables. Both of these formulas have a minimum degree of n, but the minimum PDL size of square majority is exponential, and as such, the proofs are exponential. And the minimum PDL size of the row formula is just linear. So we have shown that with square root of n, with a degree of square root of n, we can't really show anything. If I go a few slides back, well, here, you can see we have this case. We have this k squared over n. So if our degree is a square root of n, we don't really know anything here. But it also shows that it's not just too weak, our limit, because it doesn't go any better, because there are just formulas where it's still short. Now I've talked a lot about the subfields of C with the parity formulas. If we have some finite field fp or fp to the k, it doesn't really make a difference. There's a different thing we can do from these PDLs. In fact, we can extract AC0P circuits from PDLs over finite fields. And as such, for AC0P, there's a lot of lower bounds in literature. And these lower bounds directly yield lower bounds for the PDLs, and as such, directly yield lower bounds for our QPC. Now we have the mod formulas again. And if P and Q are distinct primes, then mod Qn is also difficult. It requires large circuits. That's an old circuit result. If they are the same, we have already said it's not a case. And there's also this balance formula, which is defined here, that just says if exactly half of, not minimum half, but exactly half of the variables are set, then it is true. And this balance formula is actually difficult in all finite fields. However, I don't think I've written it here, but it is simple in subfields of C. You can just add all the variables minus n half, and that's 0 if and only if exactly half of the variables are set. These results together give a nice incomparability result. So if we have three different versions of QPC. We have QPC over C, over FP, and over FQ, where P and Q are distinct primes. And the Q balance function is easy in QPC over C and difficult over finite fields. Contrary, the Q mod function is easy if and only if the primes are the same, and else it's difficult and over C as well in subfields of C. So to conclude, we have given this tight characterization of QPC by these PDLs. We have shown a size degree relation for QPC using these PDLs, which is given here, or a similar relation just for the PDLs themselves. And we have used these results to get lower bounds for majority for any field, and for mod Q for subfields of C, or for finite fields with another different prime. This we have used to show the incomparability of QPC over different fields. Thank you.
Questions?
Hello. All the formulas that you've considered are bounded alterations?
Yes.
Have you explored polynomial calculus for unbounded QBF?
We have not explored it yet. So we know that our characterization with these PDLs does not hold, but we haven't explored it any further.
Do you have any comparison to existing system, even with bounded alterations?
I mean, it strictly simulates Q resolution or QU resolution. It is quite simple to see that you can just simulate every single line of it. And yes, I think that at least with finite fields, these mod formulas should be are definitely difficult for QU resolution. As such, it's really a strictly stronger system. But for different, I don't know.
Just out of curiosity, the different fields you considered, finite fields, and then what you said, subfields of C. Do you have a more abstract characterization? If you now take arbitrary fields, can you say, or degree, 0 degree, whatever? Is there, or haven't you thought about that?
Not really. So we know that these maturity formulas, they are really hard for over any field. But for the rest, we didn't look any further than the finite fields and the subfields of C.
So here, do you think there is some server can build upon the QPC, this calculus for QBF?
Sorry, I didn't understand.
To have a server based on this?
No.
Okay.
That is just a purely theoretical result for now.
And let's say in QBF solving, usually we have the resolution part for conflict learning.
Yes.
And we have, let's say, consensus proof for the satisfying assignment learning. And is there a corresponding consensus proof in this formulation?
At the moment, we just looked at really false QBF and only this part, so no contrary part.
Thank you. Other?
Can you tell what is the motivation to explore polynomial calculus for QBF?
It is more of a general motivation to see the different proof systems that we know for the propositional case. In the propositional case, there are such nice schemata where you can really see, okay, this proof system and this is stronger than this one, and we have such a nice such a nice choice of proof systems. In QBF, there's not so much of this. So it is purely to research to further this.
More questions? If not, let's thank the speaker. So our next talk will be on proof systems for QCDCL with dependency schemes. And the speaker will be Abhimanu Chahari.
So, this is fine. Yeah, hi. So I'm Abhimanyu. So I'll be talking about proof systems for QCDCL with dependency schemes. This is joint work I'm doing with Meena, and Meena already introduced the QCDCL proof system as such. So I'll just briefly reintroduce and talk about the work that we did. So the QCDCL is basically the quantified extension for the CDCL algorithm that we use for QBFs, and it's basically the algorithm tries to decide whether a QBF is true or false. And the algorithm basically works on two important principles, which is propagation and then learning something from the propagation and going on till we either find a truth or the falsity. So I'll be looking at it mostly for false QBFs. So just from the perspective of false QBFs is what I'll be focusing on. And we formalize the refutational proof system for this QCDCL algorithm. So this was first formalized, the system by Best, Olaf, and Benjamin in their paper. And so they formalized it as a sequence of triples. So we have a collection of trails. We have clauses which we learned corresponding to these trails, and for every clause we learn, we have the corresponding long distance Q resolution derivation for that clause. And we say that the derivation is a refutation if we can learn the empty clause, and the size is given by the length of the trails. So this is basically the QCDCL proof system that we talk about. And in general, we focus on trails. So what we mean by a trail is basically an assignment to all the variables, and it either ends in satisfying all the clauses, or we have a conflict, which means that either the assignment has falsified some clause, or we've assigned opposing polarities to the same variables due to some reason. And how this goes about assigning is already, as Meena talked about, is unit propagations, or the pseudo unit propagation that she said, which is basically if we have a clause at any point in the trail, and it's the universal reduction of it is just a unit existential, and we propagate it, set it to satisfy. And at every point in the trail, we may not have some propagations. So at some points, we may need to make some decisions. And so usually, there are many ways we can make decisions. So one way is level ordered, which we just focus on the quantified prefix order. So anytime we have to make a decision, we look at the first variable, which is unassigned according to the quantified prefix, we assign that. Or we can say any order, which is we just assign any unassigned variable, we decide it in some polarity and go on. And clauses are learned from the trail, which ends in a conflict, and we use long distance resolution and reduction, universal reduction, to learn some clause. And dependency schemes. So again, looking at it just from the perspective of false formulas, we talk about the dependence of an existential on a universal. So we say an existential X is dependent on a universal U if, looking at it from the two-player game perspective, if the existential player could win the two-player game, he could win it by choosing a value for X without knowing the value for U. Then X is independent of U. For example, if you just look at this toy example at the bottom, on the left-hand side, for all U there exists X. The existential player can win the game, but the existential player wins the game by setting X as opposite of U. But on the right-hand side, the existential player can set X equal to 1 and always win the game. So on the right-hand side, X is independent of U. Here, X is dependent on U. So this is, and why do we want dependency schemes? Because in general, in the QBF proof systems, we have reduction, which says if U is to the right of X, we can reduce X to get X. But if it's to the left, we cannot. But in the addition of a dependency scheme, if U is to the right of X, we can still reduce. But if U is to the left of X and X is independent of U, we can still drop the U and get X. This is basically a relaxation on the quantified order. So this is the advantage of dependency schemes. So one example is the RRS, or the reflexive resolution path dependency schemes that I studied. So given for this formula, this small program, trivially, if you're looking at existential depending on the universals, the T's depend on the U's. But if you look at this resolution path RRS scheme, we say it's empty. So what is this resolution path dependency schemes? It says UX belongs to the dependency scheme if there is a resolution path between UX and U bar X bar, or UX bar and U bar X via existential variables quantified to the right of U. And so what is this resolution path? So this resolution path is basically if I have a sequence of clauses, and I pick one literal from the first clause, I pick one literal from the last clause, and I have these literals in opposing polarities along the way. So this I have U1 I have U1 with T1. Oh, sorry. Yeah. I have this U1 T1 bar T. Oh, sorry. This should be T1 bar. This is a typo. And T2 bar. And then again, it's U1 T1 T2 bar. Again, it's a typo. So it's T1 T1 bar from coming from the last clause in the formula. T2 bar T2 and so on. And I say that this is a resolution path which says U1 T1, but that is not because I'm using a universal variable. So what I'm focusing on is from U to X, I can form a path using existential variables in opposing polarity, only existential variables and in opposing polarities to the right of U. So this is just a particular dependency scheme, the RRS dependency scheme. And so the main idea I'm going to talk about is adding dependency schemes to QCD. So in general, what dependency scheme is not important, but in general, how can we add dependency schemes to the QCD cell? So in general, the basic vanilla QCD cell system, it focuses on level ordered, if you restrict decisions on level order. It may not always be necessary, but suppose the vanilla version restricts decisions on level ordered. If we have a dependency ordered, we can relax that and say it's a dependency ordered decision policy, where we can say X can be decided only if all other variables that it depends on have already been assigned in the trail. In level ordered, I would say that all variables to the left of it have been assigned. Here I say that all variables it depends on have been assigned. It's a slight relaxation on the order. The other place I can add dependencies is to propagation and learning. What I mean by that is, in general, a clause is unit when I say that the universal reduction of the clause was unit. Now I say the universal de-reduction of the clause is unit. So it's an extra power to the universal reduction. And when I'm learning, instead of just long distance resolution and universal reduction, I use long distance resolution with dependencies and reduction with dependencies. So I'll highlight a slight example later to illustrate the difference. And the third way is just basic pre-processing, which is given a QBF, I just apply a dependency scheme to it, get a reduction of the QBF, and then perform QCDCL on it. So now the first way I'll focus on is I restrict my QCDCL to level ordered decisions only. I will not talk about any relaxations on the order of decisions. I'll talk about dependency schemes in propagation and learning and in the pre-processing stage. So what do I mean by dependencies affecting the propagation and learning? So in general, if I have this formula, suppose I did not have any dependency scheme and I wanted to create a QCDCL trail for this formula. So the first initial stage, there is no propagation I can do. There's nothing which is forced to be set. So I start off by making a decision according to the level order. I suppose I start off by setting x1. That doesn't force anything. I set x2. That doesn't force anything. Finally, when I set u1, does the second clause in my formula become unit, which I'm then propagate to t1, which propagates from the last clause t2 bar, and finally the fourth clause is falsified. So I reach a conflict in my trail, and from there I can do backtrack and learning via long distance resolution. So these clauses in blue are my potential clauses I can learn, and I can choose to learn any one of them. So from this trail. But when I allow dependencies, the things in propagation, the things changes. The moment I decide x1 again, from the second clause, it becomes u1 bar t1. But according to my dependency scheme, u1 does not depend on t1. So t1 does not depend on u1. So I can drop my u and I can propagate my t1. So propagating my t1 again propagates my t2 bar from the last clause, and then the third and fourth clause both reduce to x2 u2 and x2 bar u2 bar. So the u's can be dropped by reduction, and I can propagate both. So I reach a conflict. Here it took me 3 decisions to reach a conflict. With the addition of a dependency scheme, just one decision allowed me to. So ideally, we want to say in a trail, maybe fewer decisions is better because we are propagating, forcing more stuff. So maybe it should help us get a conflict faster. So this is the difference between having QCDCL with no dependency and with dependency in propagation and learning. So, but how does it affect? So when we actually study the systems, when restricted to level order decisions, it's not necessary that always adding dependency schemes will give me an advantage in propagation. So we study these three systems here, focused just on level ordered QCDCL with dependencies, either just pre-processing it, having it just for propagation and learning, or having it in both cases. So the results show that these three are pairwise incomparable. What I mean by that is there are formulas which are easy by polynomial size repetitions in one, but require exponential size repetitions in the others, and vice versa. So so adding dependencies in one way may sometimes be better than adding dependencies in two ways or in another way. And all these three sets of formulas, adding dependencies in general may also be worse than having no dependencies at all, which is just the QCDCL system there. And it's sometimes better, sometimes worse. And an example which actually shows why adding dependencies when restricted to level order is bad will come from here. So the trapdoor formulas were introduced in the Olaf and Benjamin's paper, which was shown to be hard for level ordered QCDCL proof systems. So why it's hard for level order when we have no dependencies is that PHP denotes the pigeonhole encoding of the pigeonhole principle, which we know is hard for resolution. And so here, because looking at the quantify prefix, we start off by making a decision on a y. Any decision on the y variable, because the u's are quantified after x, forces a propagation of the x from one of the two clauses. So that by the time I decide all the y's, I propagate all the x's, which forces a contradiction in my pigeonhole principle. So in this first case, any QCDCL trail will always hit a conflict regarding my pigeonhole principle clauses. And we know that pigeonhole principle will, and we end up refuting the pigeonhole principle propositionally in resolution, which makes it hard for basic QCDCL. But adding dependencies to it, it becomes easy, because the moment we decide the first y, because the w's are independent of t is independent of w's, the moment a y is decided, I propagate a t and a t bar, and I can reach a conflict from the four tautological clauses that are there at the bottom in the third row. But again, so this is when an advantage. But the disadvantage comes from, suppose we just shift the quantification of u earlier and add a single clause, w bar t bar. Now this formula becomes easy when there are no dependencies, because since the u's are quantified before the x's now, deciding a y does not propagate anything. After my y's, I decide a w, and I can get a conflict from the third row. But the moment I have my dependencies, since the w's, t depends on w, there is no reductions there. The moment I decide a y, I'm forced to propagate an x in the case of a dependency, which gives me a conflict, which is the same problem I had in the top formula without dependencies. So in the top formula, the problem that dependencies avoided, they cause the same problem in the bottom formula. So this highlights that adding dependencies may not always be an advantage when restricted to level ordered systems. So here, here we have considered systems without cube learning, which Meena mentioned. So cube learning is only necessary for showing truth, but it's proven that even for refutations, cube learnings add strength to the formula. So how cube learning differs from without cube learning, something Meena already said, is now we just don't have clauses. We also can propagate cubes, we can learn cubes, and that's it. So we have the long distance QRes and clauses, we have the complete dual, we have cubes and existential reduction and term resolution to go along with it. So adding cube learning just to QCDCL, we know, is a stronger system, even just from a refutational perspective. But what happens when we add dependencies to these systems even if when we add dependencies, even with cube learning, these pairs of systems remain incomparable, and they still remain incomparable with basic QCD-CL. So if I have QCD-CL, just adding cube learning gives me a stronger system. But to QCD-CL, if I add cube learning and I add dependencies, it's not necessarily always a strong system. That's what. So it might be that adding dependencies along with cube learning is a disadvantage from having neither. That is something that we highlighted. And another interesting set of results were basically directly we know adding dependencies, cube learning to QCD-CL makes it stronger. So if we have a dependency plus a QCD-CL system, adding cube learning to it is again a strictly stronger system. But when the dependencies are added in different manners, the strength is again incomparable. So adding dependencies in different manners, but one with cube, one without cube, are again incomparable. So this is a basic quick gist. And moving away from RRS, there's another dependency scheme, which is the standard dependency scheme, which lies somewhere between the RRS scheme and the trivial scheme, which is for which we have actually, it's more interesting because we know that this scheme is weaker than the RRS scheme. But for this scheme, we've only been able to show one set of results, that adding the dependency scheme is an advantage. But we haven't been able to show that adding the standard scheme to be a disadvantage is proven to be much harder to show than the RRS scheme. So this is something we are still working on. But what we have been able to show again is that adding dependencies versus adding cube learning is incomparable. So this is all this was all just restricted to level ordered systems. And the final thing for the level ordered system was, in level ordered systems, how the dependency scheme is added, it makes a big difference to the strength of the proof system. It is not in fact that adding dependencies in one particular way is better than adding it in others. And it is not that one particular dependency scheme so far is better than others. So each dependency scheme can be shown to be an advantage or a disadvantage in some cases when we just focus on level ordered systems. So standard versus RRS are basically adding them is completely incomparable with, irrespective of whether I have cube learning or not. So this is what we felt is a restriction of level ordered. Focusing on level ordered creates all these problems. So moving away from level ordered, if we try to look at a more general decision policy for QCD-CL, which we call the decision order. So we create a soft relaxation. We are now allow decisions in this de-ordered scheme. So here the propagations, again, we don't care whether they are whether they use dependencies or not. But what we can say is that they're with the dependency, it's definitely at least always as strong as level ordered, because any level ordered decision is included in a de-order. So a level ordered decision policy will always be a de-ordered policy. And in fact, there's a formula to show that de-ordered is strictly stronger than level ordered. And why de-ordered is now interesting to study, because the basic trap-based lower bounds, where we forced the dependency scheme down a path, do not work when we allow dependencies in the decision policy. Those basic trap-based ideas do not work anymore. And we know that this is at least as strong as LDQD resolution, because those are the proofs we extract from this. But the separation is still not known. And this formula basically highlights, there are two copies of PHP and the tautology on Z1, Z2, so we call it 2 PHP and Z2 CT. So these are basically hard for level ordered, but allowing de-order makes it easy to refute by jumping over the PHP block. Because if we for this formula, if we focused on level ordered, we would have to start by deciding U and then going into the pigeonhole principle. But the moment we allow by freedom of order, we can directly jump to the second part of the formula, which is completely disjoint from the part, and refute it to get a short proof. So this is the advantage of dependence order. So this is what we're studying now. So I'll conclude by saying we studied adding dependency schemes to the QCDCL proof system. And when restricted to level ordered, we see that basic trap-based lower bounds for hardness work, and adding dependency schemes fluctuates from giving strength to making it weaker. And then finally, we move to dependency schemes in order, and they are provable at least stronger than level ordered system, but we're still working on exactly characterizing the strength as compared to long distance resolution. Thank you.
Questions?
Hello. When you say you add dependency schemes, generally, like we just saw a proof system, like polynomial calculus plus for all reduction. It is optional. It is not necessary always. Like you said, adding it is sometimes worse, right?
No, so
So-
what adding dependency schemes here means the rules modify. So instead of when you have universal reduction, in general you reduce everything you can reduce. Here,
No, if it is creating worst case, you don't need to, right? If you get a easier proof some other way,
no, but
it's just a choice.
no, but for the way we define it for reductions or for resolution, whatever you can reduce, you have to reduce. To I That's the way it's defined. So in
That is
general, you
because
can
it's
always have
advantageous.
relaxations, weakenings. You can always choose not to do stuff, but in the basic definition, when the way we've defined it, adding a dependency means whatever you can reduce, the smaller you can make it, you always try to make it smaller. In a sense, it's a greedy way of trying to prove. So it's not that way. It adds more non-determinism. This adds more restrictions. Whatever you can do, you have to do to make it smaller. So in general, yes, if you say that I add dependency scheme, but I only choose to use the dependency scheme when I want, that way it won't be a disadvantage. But if you say that if the dependency scheme is there, you have to use it, then it will be a disadvantage.
Yeah, then it will become a little non-deterministic, but then you can analyze its complexity more better, right?
Then you can say that it will definitely be better. Then you can say if you can suppose, yeah. So then you can analyze it differently, yeah.
So maybe I missed that point. Most of your lower bounds and separations were for level order.
Level order,
decisions.
yes.
So do you have any lower bounds at all for the decision policy when you follow the dependency scheme?
For the decision, no. The lower bounds are all long distance lower bounds. No,
Okay.
nothing apart from long distance.
Okay. And the formulas on which you have the separations, I mean, you mentioned these trapdoor formulas and
Yeah.
variation of that. Do you also have other formulas that don't import resolution hardness, like these CR formulas that you can use for it?
Possibly there is, for one of the cases, there is a slight modification of the equality formulas. So there's no propositional hardness imported as such. So for one of the separations, there is a modification of the equality formulas which is used. But for CR, I haven't tried, so I don't know for CR where the hardness lies. But so this was just one of the examples. So in some cases, there are the modifications of the equality formula which make it hard, but most of them are propositional PHP based.
Thanks.
Other questions? If not, let's thank the speaker.
Okay, I just take this microphone. Where do I find my slides? Okay, so first of all, let me thank all of the speakers for this exciting talk. I think today we had a very nice mixture of the presentation of recent results on theory and practice. And yeah, it is very nice to see that such a lot of different directions in QBF research and in DQBF research are taken in order to make some progress. I would like to use the last minutes of this session to discuss some issues that relate to recent research and that are quite pressing. And I would be happy to collect ideas, maybe also get in touch with people who are interested to contribute. And this relates to several aspects. In particular, one main point that is quite urgent is the QBF lib. Maybe most of you know QBF lib as the community portal of our community, where we collect benchmarks, tools, yeah, maybe also some links to literature. Yeah, what is also there are the standards. So the QCIR standard is in principle published there. The QDymex standard is published there. And maybe you have seen that for some time the QBF lib is offline. This is because of some technical issues of the person who is hosting it. Yeah, and I have to re-ask him again. This is Luca Bulina, but it seems that he has some administrative issue with his university regarding the security of the server, and it's not so easy to set it up again. And yeah, this is really bad that we don't have access to our benchmarks at the moment. And it's a lot of more things that are on QBF lib, for example, results of the past evaluation. But when one looks at it, it becomes also obvious that the structure of the QBF lib is not optimal and that it's from the design quite outdated, and it's not really easy to find data and to access things. So maybe this might be a good opportunity to redo things and think about what do we need, how do we want to organize things, and so on. Yeah. Yeah, and also the question is where to host it. Yeah, maybe it's not so good to go again to some university where we have then again introduced the dependency on a person. Yeah, I mean, in principle, I could host some things, but I'm not sure for this reason if this is a good idea. Maybe we can kind of come up with some more general approach that has more that allows easier maintenance and also allows it for international collaboration. Yeah, because if I put things on my university server, then there are still restrictions. Who can do the administration and so on. This might not be a good choice. For example, we could use some public repository, or I will then later on, when we talk about the QBF competitions, talk about some suggestion that might give us some flexibility, and maybe we find a way also to do it for the older data. Yeah. Yeah, if you have some idea or want to say something, please interrupt me. I'm not sure how interactive this session will be if I just give the presentation, but feel free to give some comments and say something. Evansha has an idea.
I think we have discussed a little bit before as well with regards to benchmarks. I mean, if there are benchmarks, we could put somewhere like Zenodo. You don't need to change much and everyone can access.
Yeah.
Now the tools is a bit harder problem. I have used many tools and it's quite hard to install them. Maybe something like PYSAT is good, but maybe it takes a lot of effort to do it. But at least some kind of containers. So planning competitions, they have it. So every tool has a container, you can just use it. You can also put it in GitHub or somewhere.
Yeah, so Zenodo is exactly the direction which we will suggest for the competition. And regarding the tooling, this is exactly a very important point where we are quite stuck at the moment. We observe that a lot of people are using C3 because the QBF tool chains involve some challenges to install. And for this reason, a PhD student of mine, Mark, and another PhD student, Max, they worked on QBF, and this is currently published. So there are many QBF solvers should be accessible in a uniform way via a joint Python interface. This is the one thing we worked on. The other thing is at each car we had some tool paper on a tool called Bulguru. Maybe you know.
Yes.
And this is a very flexible infrastructure for handling formulas. Yeah, so for example, Zetin transformation is implemented such that you just can use it out of the box. Different formats are considered. Yeah, so you don't need to do this transformation to QDimex directly, but we support different formats that make the usage simpler. Another thing we have is, and this we have quite long, and this is not so much known, but we have an online tool which is called Limbul on the Go. Limbul is originally a SAT solver developed, or a SAT solver front end developed by Armin for educational purposes. So it has this very old Bool syntax, which maybe some of you know. So we have non-CNF format with and pipe for and or, and exclamation mark, and we can arbitrarily nest formulas. We have implication, we have equivalence in this format, and this we extended also to QBF, yeah, so to Brinix QBF, and we have this web interface where people can paste in their QBF, and then for small problems, this works pretty well. This is something what we also use in teaching, and this turned out to be very useful, but we did not really promote it in the community, and maybe we should also think about making such efforts more visible. And I guess others have such things as well that they use in teaching, and I think we should set also more focus on things like that, and this relates to the tooling issues.
Just one more in the benchmarks. I think we need reproducible scripts.
Yeah.
So I was trying to use so many benchmarks, but you don't know what the benchmarks do. We just take the benchmark and say we run them, but it would be nice to have reproducible, some kind of reproducibility.
Yeah.
I mean, there are many benchmarks which are solving the same problem, but if you want to compare them, there is no way to do it.
Yeah, exactly. And this is also an issue with the QBF lib. I mean, there are benchmarks which are 20, 25 years old, and it's really hard to reproduce where they come from. I mean, Luca put a lot of effort into getting this, and for all we have that are somehow left, we have some references, but the people who produce them are often not anymore in QBF research, and we don't have access to the generators, and it's really hard. I mean, I know this also from my own work. I also produce such things. It's really hard to reproduce, and I'm at least now working on getting my things reproduced and document this properly, because it's really hindering when we don't have that, and we need to do this in a more structured way in order to make experimental progress. Yeah.
Yeah, thank you.
Totally agree with that. Yeah, so the QBF lib is the first issue, and I'm having something in mind, like going to some public repository and then build up a very basic web page, and then using things like Zenodo in order to collect things. But this needs to be worked out in detail, and if somebody's interested in that, I'm happy to get in touch and build also a group for or a team that works on that. The second thing is the future of QBF Workshop, of the QBF Workshop. I mean, we have years where we have a lot of participants and a lot of contributions. So this year it was quite nice and good. But we also have years where we have fewer participants, fewer workshops, and the question is this workshop format as we have it the right format? Should we continue like this? Do we want to have a different organizing team? Do we want to extend it? I mean, at the moment, most work is done by Friedrich and me. We're grateful that you joined the team. The third organizer is Yubi Chen. He's also doing some things in the background, but he's not very active in our community. He's more in CP community and different communities. And yeah, it would be nice to have maybe someone on the board who is more active in our community. We had Florian Lonsing. He's not working on QBFs anymore, so yeah, we could also discuss this. And also for the QBF workshops, the question is, shall we continue with this format, or do we have new ideas? Can we do something more interactively? What would be appealing? I mean, yeah, this year it's really nice to see so many people, and this encourages me to continue like this. But yeah, sometimes it's also sometimes it was also difficult in the last couple of years. So I also want to put this in the room that we rethink about this. Yeah, and then the last thing is about QBF competitions. So this year we don't have any because there is not so much progress to observe. There are very few solvers at the moment that come up. I mean, I have the feeling at the moment there is more ongoing in DQBF research than in QBF research. But my experience says that there will be more in some future. I mean, we observed. I mean, I'm now in this business for about 20 years, and there are waves. Yeah, so there are times when fewer PhD students and people work on solvers, then we have peaks, or we even have more contributions than the SAT competition, and then it goes down again. So I'm not really worried about this. I think it will come and go. The question is how, and now we're really in a valley. Question is how can we come out of this? How can we make it more attractive? And again, how can we make it more sustainable for the future, that we don't run into these problems we have now with the QBF lib, that we in future can access results better. Yeah, and a point I want to mention is that StarExec will be shut down in the future, and we also need some ideas where to run it. I mean, if we have it at this scale, we can most likely locally run it in Linz, or maybe we find some compute infrastructure at some friend universities. But also here we would need some ideas, and I think that might have similar issues. And yeah, not sure what to do about this. My PhD student Simone Heisinger, who could not join today, worked a bit on how competition could be organized in the future, and how we could organize the submission process. I will quickly go over this. And yeah, what I'm not sure about is that if it makes sense at the moment is to have a deadline with a call for competitions, for benchmarks and for solvers. Maybe it would be better for us as a community to have something continuously, so where we regularly ask for submissions and then update the results, and only when we have the feeling that there are enough people actively working on it, then we organize real competitions. I mean, these real competitions are important when there are a lot of people, because then it's fun to have such events, and people are happy to receive prizes, medals, certificates. Yeah, this is really nice, and this is something we need to have to honor the people who spent the time in the implementation. If there is not so much ongoing, then we could maybe do something continuously. And what we want to consider is and this is what Evangelos has talked about is to have the formulas submitted via Zenodo, because then it's better under the control of the submitter. The person gets all the credits for it. Copyright issues are clearly settled, because this has also been a bit vague. We will have, or we already established a QBF community on Zenodo where things can be collected under a joint umbrella. So each submission has an own upload, which is then under the control of the person who submits the benchmarks. We have interesting metadata, so this is also then collected in a uniform way. And yeah, we can also control the accessibility. We can first have a restricted visibility, then we can evaluate the benchmarks, and then we can set it to visible, and then it will be archivated and will not be lost. And this is one thing we are considering to deal with the benchmarks. And in a similar way, we hope we can proceed with the solvers. And also here, Zenodo is a platform that is nowadays used by many people who submit artifacts with their papers, and with this specific version is archivated. And we think this will then allow us to collect links to software which is permanently available, and which we can test, where we can also get feedback maybe, and which we then can also put on a web page, and which will be there and not disappear, because this is really an issue that we have a lot of lost tools, and that many approaches actually need to be re-evaluated and re-implemented. And with this, we would solve this problem. And Dylan, yeah?
EasyChair went private, Python, blah blah blah, went private. So suddenly these they disappear. These
platforms.
Yes, and licenses and change, and so possibly that cannot be avoided. But it just that's how the world is. But because I'm not aware of this Zenodo, could you just say a few words of that?
Zenodo is nowadays gaining more and more attention for collecting artifacts.
Who's running it?
I'm not entirely sure. I mean, we can have a look. I'm not entirely sure who's behind it, but it's something EU funded, so it's publicly funded. And I should have prepared a slide on that. Actually, I don't know it by heart, but I think it's reasonably trustful. And I think this goes also with this data protection, data reproducibility things, that the EU is very strong behind it. So, for example, in Austria, we have to do data management plans for publicly funded projects, and having our data and our sources at this Zenodo platform is approved by the funding or agency, which is a sign for me that this is a trustable thing.
Sounds reasonable, yeah.
But I mean, for several reasons, I have to take a closer look, and this is just one suggestion. If someone has concerns, I'm happy to learn about it and discuss it. But from my current point of view, this sounds as a reasonable choice. Yeah, but next time I make such a suggestion, I should prepare on the platform also. Sorry. Yeah, and we have then this Zenodo community, which is already set up. This gives a joint umbrella for the submissions. We can evaluate it, and we can say what fits, what does not fit. And there the link is missing, but we'll have a joint a link where we can collect things, and then this has the advantage that we do not have to provide any customized thing, but we can just use this very easily. And I mean, yeah, I have used this for several artifact submissions. It's really easy to use. If Ansha has good experience with it, and I think something like this is definitely a way how we could go. And what I would also like is to have a nice web page which is very easy to maintain, and where we point also very simple pointers to starter, that people become aware that it's maybe not the best choice to start with C3 for going with a QBF, so for prototyping with QBF, but that we also can provide the infrastructure because we have more advanced techniques than one would find in quantified bit vectors. We evaluated this actually, so this is a funded claim, and people should use the technology we have. Yeah. Okay. This is the things I wanted to point out. Maybe, yeah, you have some feedback, some ideas. We can discuss now, or directly, or you can also contact me. Thank you. Yeah.
Solvers, we might need containerization somehow. Otherwise, everyone will spend time to install it. People have different OS, different. I think we also need to stress. You need to containerize it. You just go to the container, run it.
Yeah.
I think that's important.
Yeah. So this we now have with this PyQBF artifact. I can give you the toy.
Yes,
and then we have it actually on a Docker image. It's really easy to install. I tried it out yesterday, and it was 3 clicks, and I had a QBF environment running with different solvers and evaluation scripts, and yeah, very nice.
A few years later, or else I would be very happy during my PhD.
Yeah.
Thank you.
Yeah, just one feedback on the second point you mentioned, the QBF workshops.
Mhm.
I really think that these are a great format to bring together the community. So I have really enjoyed these over the past couple of years, and I think it would be really a loss if these were discontinued. I mean, I completely agree that organizing teams, I mean, evolve over time, things might have to be updated. But in general, I don't see anything that needs to be changed fundamentally. I mean, it's an imperfect fit to affiliate this with the SAT conference, to have it in advance of these conferences in this workshop block. It's also a perfect thing, in my opinion, that we meet once a year as a community to discuss the latest findings. Because, I mean, for instance, today there were a number of papers that were presented at different venues, but I think it's really important that these get into the QBF community. I mean, for instance, the paper that Luke was presenting will be presented at MFCS next week. That's good, but it has to also be presented to this audience, and I think this is exactly the right venue and format for it. So I think we really should continue it. So I would be really in favor. And regarding your other point on QBF Lib and the repository. I think you make an excellent suggestion there, that we should have it on some public repository. I mean, one thing that also would come to mind is the SAT association pages, but honestly, I don't think we've got the resources to maintain it. That's simply an issue.
It's also my concern, because yeah, I know a bit the backgrounds, and
yeah, exactly. So if there is like a dedicated team that caters for it, and then have it in an independent place, that sounds very good to me.
Okay, thank you. Okay, yeah, so you have some takeaway thoughts, and yeah, if something comes up, please really feel free to contact me. Okay, yeah, then we come to the end of this workshop. Yeah, thank you very much for attending and joining today, and we hope I really hope we have an interesting SAT conference, and I'm looking especially forward to the QBF talks. I think there are some very nice works. I'm really curious about. Thank you.
As always, I'm here again, the same familiar face, here to remind you about the various security protocols. At the same time, as you know, there are parallel workshops going on. If you want to, you can